So last weeks we did many examples of greedy algorithm, greedy paradigm. So we did especially this MST algorithms by cut and by cycle. Given a weighted graph, you want to find minimum spanning tree. And then we also did this problem of mobile towers, placing towers so that all the houses on a line are covered in the minimum towers, minimum number of tower installations. So in all these examples, we saw that there are multiple policies or strategies you can use, and only one of them you can actually prove. Okay, the other strategies, there is always a problem. So you have to pick the correct strategy, and then you have to prove that it actually gives you the greedy. It will be a greedy strategy, but you have to show in the lemma that it gives you a smaller instance. Okay, which if you solve, then you can solve the original instance. Then we finished up with this exercise covering intervals problem, okay, where you have to, in the exercise, find this greedy algorithm. So here you are given intervals on a line, and it's kind of opposite to the job scheduling problem. So here you don't want to find disjoint intervals, you actually want to find few intervals so that they intersect with everything else. Okay, you want to find the set B, which is a cover, and it has to be the smallest. So here again, as a hint, this finishing time, the finish time will be a key parameter. So you sort according to finish time and then make your decisions. So you can try the strategy and give the lemma. Any questions till now? Okay, so then we will solve a harder problem and a very, very practical one. Again, it will be a adaptation of greedy paradigm. So this is the shortest paths problem. And single source. So here you are given a weighted directed graph, and you are given a source vertex, which is the key vertex S, and you want to, and all the edges are, you can think of them as roads with kilometers written on them. So from S you want to find shortest distance in kilometers to every vertex. So something like this was given in one of the quizzes, but at that point you did not know this algorithm, so you could not have given this. This is a much faster algorithm. What is the closest to this that you have seen, which was the answer of the quiz? The closest algorithm that you have seen till now for this? Yeah, so BFS is the only thing you have seen. But in BFS you assume the distances to be 1 kilometer. Either 1 or 0. 0 means that there is no edge. So in the quiz you were supposed to modify the C break it up into edges of length 1. That is the solution, and then do BFS. Which is not a practical solution because the roads may have hundreds and thousands of kilometers distance. So then you will be putting, instead of one edge, 1,000 edges. So you don't want to do that. You want to give an algorithm that doesn't look at the distance. It works for all distances. So you are given a directed graph. And positive edge weights. So we see it as a weight function, W, from the edges to natural numbers. and you are given this vertex S, which is the single source. Now, of course, you can repeat this algorithm for all the vertices choices of S, so that also will work. But we still will call this single source algorithm because it is good for one source. And if you want to do it between every pair of S and T, then there are much faster algorithms, which you will see in advanced courses, advanced algorithms. So there is single source and there is multi-source. So in this course, you will only see single source. Anyways, that's the first one. So in the output, you want for all the vertices shortest distance delta S comma V and the shortest path P S comma V. Okay, so this is your output, the delta array and the P array. So delta is an array of integers, positive integers. It basically, delta V just gives you the Vth location, gives you the distance, shortest distance from S to V, which clearly is a unique integer. Shortest distance is always a single number. Shortest path, there may be many shortest paths from S to V. So PV in the array in that location, a path will be stored. Some path on which if you add up the kilometers, it comes out to delta SV. Okay, so that is what is needed for all the vertices simultaneously. Is this clear, the input output? Okay, so as I said, what we have seen before is for W equal to 1 constant, that is WE is equal to 1 for all E, you will just do BFS. BFS was for exactly this purpose. Okay, so on S it will start this ripple and breadth first search. So it will find all the cities in 1 kilometer, 2 kilometer and so on. Okay, so if edges are, every edge is 1 kilometer, then you can just do BFS. And in the quiz, we modified this to W equal to some other constant. Like constant can be 10 within 10 kilometers. So 1 to 10 are the numbers. So in that case, you break up an edge into 10 parts and then do BFS. Okay. So that is fine for small weights, but not good for big weights. So we want to solve this now realistically. So when the weight function is arbitrary, then what should you do? Is there a way to give an algorithm which is much smarter than BFS? So note that as always, brute force exists. So either you can, so idea 0.1 is for try all paths. From S to V and pick the min. Now how many paths are there from S to V? You are basically picking a subset of edges. Right, so this may take how much time? 2 raised to m time. and usually M is very big. So like in a state or in a country, there are thousands of cities, and then between every pair of cities there is a road. So that's like 1,000 square. So M is more than 1,000 square, right? So your 2 raised to M is incredibly large. So this idea is useless. You cannot stop this algorithm. Second is that you can reduce to W equal to 1 by cutting the edge. Right? So this was the answer for the quiz. You have an edge of weight 10, then you break it up into 10 edges, and then do BFS. But this again will be very slow when the weights are very large. So we'll do something more clever than this. So we'll go back to the ripple idea. So we have been using the ripple idea many times in this course. At least 2 times we have already, 2 or 3 times we have used, so this will be the 4th time. But here it will be more sophisticated. So we'll use both the ripple idea and the, let's say, BFS tree idea. Okay, we'll use both these properties to give the fastest algorithm for shortest path. So let us see this through an example. So this, let's take a decent example. So you have S vertex, then you have vertices V1, to V4, and you have V5, V6, and so on. And you have these edges. So 1 to 4 are neighbors of S, and let's say V2 to V6 there is an edge, V2 to V5, and V2 to V1. Every edge is directed and weighted, so the weights are 2, 7, 21. V2 to V6 is also 2, S to V3 is 12, S to V4 is 5, S to V2 is, this one is 3. And let's give one more 3. Okay, and then so on. So this is the graph given to you. The source vertex here is S, so you want to find the distances from S to every vertex, shortest possible. So in this maze of cities, from the point of view of S, which city is closest to S? Right, that is the first question to be asked. If you want to do greedy approach, then what is the nearest city from where you can go from S? It is V2, right? So here, so we are sure of only one vertex, and that is delta from S to V2 is exactly 3. And of course, from S to S it is 0, so that's trivial. But other than that information, that S to S is 0, the only interesting vertex that we know, both this shortest distance and shortest path, is V2. So what is the proof of this, that S to V2 is 3 and it cannot be smaller? Why are we sure of this first step? So any path from S to V2 which is other than this edge of weight 3, right? Any other path will then be, will use either 5 or 7 or 12, which is more. And then the subsequent path which it will take to come to V2 will have weight positive. So this is why we assume positive weights. Okay, positive weights is very important in this algorithm that we will present. So any path S to V2 will have weight greater than 3 as W function is positive. Okay, so it's about the positive assumption on the weight function, which tells you that nearest from S is V2, and so delta S V2 is 3, and that's the unique shortest path. Okay. So we are sure of this. Okay, this we have reached. So what can we do next in the greedy algorithm? Once you have found the nearest city, what should you do next? Nearest city to V2, sure, but remember that we are interested in finding distances from S. Mm-hmm. No, but tell me in this picture. So this picture is complete information of both S and V2. So which edge should be picked? Which edge should be picked next? Yeah, so S and V2 we have picked already. So this we have picked. What should we pick next? Either V4 or V, yeah, so that's the thing. So we don't want to look back, because if we look back, then we are actually backtracking. And this is not what a greedy algorithm follows. So the greedy algorithm has to be simple. So once it has reached V2, it should only look around V2 and pick something. So the way to do that is to make an observation that we can actually club S and V2 together. We can make it a mega city. So that is the first observation. So this is that V2 can be absorbed with S or in S, and then update their joint neighbors. Okay, so what will this update be? So when S and V2 become a single megacity, then this V2 to V1, for example, which is distance 2, this distance should be updated to 5. Okay, so actually push this 3 outside. So 2 becomes 5, 21 becomes 24, 2 becomes 5, 3 becomes 6. Okay, so this is how the neighbors of V2 will change. That's all. This is the only change. The connections from S to V1, V4 and V3 will not change because they are neighbors of S and we are only interested in S. So they will not change, but the neighbors of V2 edges will change. Their weights will change. So that essentially is the proof. So okay, let me then draw that again. So we are looking at S comma V2 as a mega vertex. And what do we have? So we have this edge S2V1. So let us check S2V1. S2V1, now there will be 2 edges, right? Because one is connected, S2 directly S2V1, and the other one is V2 to V1. So we have actually 2 edges. So this new edge will be as set 5. So let us draw the new ones first. V2 to V5 and V2 to V6 and V2 to V3. So these have changed to 5, 24, 5. And the last one is 6. Okay, and the old ones continue to be there, which is S2V4 with 5, S2V1 with 7, S2V3 with 12, and what else? That's it, right? Yeah, so that will be the next step. Yes, so when you see multi-edges, the natural question is, well, why are you keeping 2 roads, one longer, one shorter? So then we'll delete the longer ones, we'll keep the minimum only. That will be the next step, but in the first observation, we are only saying that update the edges. Okay, so the updated edges are these. The one with 5, 24, 5, 6. Old ones are 7, so 7 and 12 and 5 basically. Yeah. And then everything else stays as before. So these connections we have not looked at. Okay, so this graph is the intermediate graph, and then as suggested, we can do one more step, which is, let's remove the so that will be the graph G prime finally. So here it will be, the observation will be reduce multi-edge. to the single min edge. So let's do that. So this will be okay, V1, V5, V6, V3 and V4. So now we only keep 5. And 24 we have to keep because that's a single edge. 5 we have to keep. 6 and 12 are the connections to V3, so we keep 6. And we keep 5. Okay, and everything else remains the same, unchanged. Okay, so this is the reduced instance of the problem G prime achieved by the greedy step. Okay, so what the greedy step has done is, again, it first found the only vertex that it knew about, which is V2. And so now it knows about 2 vertices, S and V2. Their distances are known. And it makes them a mega vertex. And then it redraws the edges with the new weights. Okay, where the V2 that you have introduced into the mega vertex with S, those edges you have to add the 3, which is the delta S comma V2. That you add, and then you basically pre-process these edges. So this gives the reduced instance G prime. So why do we call it reduced? What has reduced in G prime? Edges may not have reduced, but something has reduced. Yeah, so number of vertices have definitely reduced. From n, now it is n minus 1. Also, one edge has certainly reduced because S to V2 was an edge that's removed. Okay, but more important is that one vertex is gone. So we are actually shrinking the graph. So it's a reduced instance achieved by the greedy step. Okay, so this is essentially the idea. So this is the this will be the adaptation of the of this old ripple idea, that the ripple will try to reach the nearest city, which is V2, and then from there it will try to find where to move next by reducing one vertex, by combining S and V2. So yeah, so what we have to show is this connection. You have to show the connection between G and G prime. Okay, the delta, so shortest paths in G and shortest paths in G prime, how are they connected? Right, this has to be proved. So let us prove it as a theorem. So pick U in V with minimum delta. Reduce G to G prime as above. Then what we are claiming is that distance metric in G, okay, the shortest path in the graph from S to V, where V is an arbitrary vertex, uh, how is this related to the distance metric in G prime? So it is the shortest distance from S to V in the new graph, where we are calling S this vertex, right? This is now the new S. So in G prime, this is the new S, the new source. So the distance in G prime from S to V, well, we have already done the plus, so there is no plus. So we are just claiming that these two things are equal. For all the vertices in G prime, in fact, all the vertices in the graph G except the ones that we have removed, which is original S and original U. Okay, this is what we are claiming in our minds, that in the greedy step, the new instance smaller graph G prime that we get, distances there from the source, new source, are the same as distances in the original graph with the old source. How do we show this? So if we show this, then our greedy step is the correct step. Then we'll proceed on this. So it basically, you can prove this by two cases. So V is essentially an arbitrary vertex in the new graph G prime. So suppose this shortest path from S to V in G prime is, there are two cases, either it is using U or it is not. Right? So let's look at those cases. So the first case is that the path in the graph G prime from S to V, I guess we can also look at the old graph. So path in the old graph from S to V uses U. That's the first case. So what can you do in this case? What is the proof that the distances are the same? So you can look at the original picture. So there, if the shortest path, let's say to V6, does pass through V2. So when you make S and V2 a mega vertex, you will get the correct distance, right? Because the distance from S to V2 is 3, that will get added to the distance there being 2 from V2 to V6. So what the greedy step that we did is correct in that case. It's giving you the correct distance. So if the shortest path does use U, then delta G prime S comma V does account for delta SU and from U to V. In the original graph. So in the original graph, if the path indeed used U, then it was correct to merge the two vertices into a mega vertex. And because we did the plus, so we'll get the correct distance. Okay, so that case is done. What if the path had nothing to do with U? then what happens? So again, in the original graph, if suppose the shortest path from S to V6 bypasses V2, what happens then? Yeah, so then our greedy step did not change any edge weight in the shortest path, because it only changes changes those which are passing through V2. S to V4 you can go with the same distance, and from V4 you can go to V6. Nothing changes. So then the greedy step didn't affect the edges on that path, which means that here also delta G prime SV is just the same. Okay, so this proves that our greedy step maintains shortest distances. From the mega vertex to all the vertices outside. Is this clear? So greedy step is done, and you can just repeat this greedy step. So you have an iterative algorithm. What is the time complexity? So the idea is just to repeat this. Yeah, so let us see your claim. What is the time complexity for this? So you are doing this, reducing the graph one vertex at a time. So there are n iterations. And how much time in one iteration? So in one iteration, you have to look at the neighbors of S, find the U, the nearest vertex, and then do this transformation from G to G prime that we discussed. So this basically will depend on the degree of S. How many neighbors are there of S, and then how many neighbors are there of U, right? So that many iterations, that many steps in one iteration. So that's around degree of S and degree of U. So which is? So this is around n multiplied by m, or well, I should say, you can do a better analysis. So n times n plus m. Okay, so there are n iterations, and in every iteration, the number of steps obviously depend on the vertices. So n times n will happen. And then when you sum up over how many degrees you saw, that is just m. Right? Sum of the degrees of vertices is 2m. Yeah, so which is why m, which is why it's plus m. It's not more than m. N square is, yeah, so why does it come? Because so this is a directed weighted graph. In every iteration, all the vertices may be neighbors. So you have n plus n minus 1 plus n minus 2 dot dot 1. So it is an AP. So you get n square by 2. So n square you cannot avoid because it's maybe, so I mean like in the setting of India, every city is connected with every city. So no matter how many vertices you reduce, you are still going through n to n minus 1 to n minus 2 plus 1. So n square will come, the remaining things you try to be clever. So that is the degree argument or the edge argument. So that depends on m. So this is an okay algorithm because if m is as big as n square, then this is order n square and you cannot do better. But now we can give a better implementation than this. So any questions till now? So this was the first idea. So we will further improve this implementation. The greedy step idea will remain the same. So let us improve this using the ripple idea in a better way. In a systematic way. So this idea is basically to do with the following property. I mean, okay, in the picture so in this picture we are actually forgetting the mega vertex, the things which are happening inside. Okay, we are just saying that S and V2 are clubbed, then maybe S and V2 and V6 are clubbed and so on. So what happens inside we are forgetting. So now we will actually get inside that mega vertex also. We'll store that information as a tree structure. So to get to that, what we have to remember is this property that, which is actually the ripple property, that if you look at the ith nearest vertex, and where we set S0 to S itself. So if you order the vertices as S0, S1, S2 dot dot Sn minus 1 according to distance, the ripple idea tries to find S0, then S1, then S2, then S3, right? So we want to do this systematically. And the property is that there is always j smaller than I, such that the shortest path from S to Si is going from S to Sj, shortest path, and then edge to Si. So this one is Ps comma Sj, and this one is an edge. Okay, so what we are saying here is that when you look at the shortest path from S to Si, any I, well, any I bigger than 1, I guess. So when you look at the shortest path from 0 to I, then there is always some vertex in the middle, Sj, such that from S to Sj there is a shortest path, and then you are taking a hop using an edge. Okay, this is the property of every shortest path. Is this clear? What the statement is? So there are two cases. First case is that S to Si is an edge. So if S to Si is shortest, well, if this is shortest, then this should be called S1. So I guess I should maybe we should just rule that out here. So I is greater than 1. Let's insert it here. So for every I 2 or more, there will be a j which is in the middle. Okay, so if S to Si is an edge, which is already the shortest path, then this is the case of I equal to 1. So this doesn't apply. And if in all other cases, what will happen is that there will be some vertex in the middle. So let me call that X. And then you are reaching Si. And let's call this path Q. So this is path Q. And this is an edge. Okay, so we are in this situation where there is a vertex in the middle. S to Si overall is the shortest path we are looking at. And just before Si and much after SS, there is a vertex X that you are going through. So what can you say about this city X? Right, so basic intuition is that why would you go to city X by a longer route? Right, to X also you will take the shortest route. So which means that S to X path, Q is a shortest path from S to X, and then you are taking one hop and going to Si. Right, so this basic observation is the proof. So then this path Q has to be shortest. Else we could get a shorter path to Si. Okay, so this means that this path Q is actually a shortest path from S to X. which means that it is in the ripple. So there exists a j such that x is equal to Sj. Is this clear? So when you drive from city S to city Si through the shortest path, then the city you reach just before Si is also, you took a shortest path to that. There is a critical assumption we are making here, which is to do with positive weights, right? So this is actually using positive weights. So this you can check where we are using the weights to be positive. Because otherwise if you take a bad path from S to X, which is not shortest, I mean those things may exist if the weights were negative, because there may be a cycle of negative weight. The more you drive on the cycle, the smaller the distance becomes, right? So those weird things may happen. So we are actually using here that the weight is positive. Yeah, then you get the lemma quite easily. And next time we'll use this to give the fast implementation.